Hello and welcome. Today we're going to dive into one of the most powerful ideas in all of data science, Bayes' theorem. It sounds complicated, but really it's just the math behind how we learn, how we change our minds and update our beliefs when we get new information.
So, here's our game plan. We're going to start with a medical puzzle that will probably break your brain a little bit. Then, we'll look at the actual formula that solves it. After that, we'll crunch the numbers together step by step. And finally, we'll see how a simplified version of this theorem became a total powerhouse in the world of AI.
All right, let's kick things off with a puzzle. It's a classic scenario that seems pretty straightforward on the surface, but, well, it's specifically designed to show you just how wrong our gut feelings about probability can be. Okay, so imagine this. There's a very rare disease, only affects a tiny, tiny fraction of people. You take a test for it, and it comes back positive. Now, the test seems pretty good, right? It catches 85% of people who actually have it. So, you test positive. What do you think the chances are that you really have the disease? Your intuition is probably screaming something like, well, it's got to be around 85%, right? The actual answer is less than half of 1%. Yeah. Shocking, isn't it? It feels completely, totally wrong. So what on earth is going on here? How can our intuition be that far off? To figure that out, we need to pop the hood and look at the mathematical engine that's running behind the scenes. And that engine is Bayes' theorem. This is the tool that lets us correctly handle new information, like a positive test result, and update our initial beliefs in a logical, structured way, instead of just going with our gut.
And listen, this isn't just some random formula from a dusty textbook. As data scientist Peter Gleason puts it, it's pretty much the most important rule in data science. Why? Because it's literally a mathematical description of the act of learning. And that's a huge deal, especially in fields like machine learning.
So, here it is in all its glory. Now, don't let the letters and symbols intimidate you. All this is saying is that the probability of our hypothesis, H, given some new evidence, E, well, it's something we can calculate using a few other key pieces of info we already have. It's just a structured recipe for updating a belief. Really, the best way to think about this is like a story. The posterior is our new updated belief. That's the final answer we're after. We start with our prior, which is what we believed before we got the new evidence. Then we adjust that belief using the likelihood, which asks, how likely would this evidence be if my initial belief was true? And we divide the whole thing by the probability of the evidence itself, just to keep everything scaled correctly. You know, a big reason people get tripped up by this stuff is they mix up the direction of the probability. Think about it like this. What's the probability of seeing clouds given that it's raining outside? Well, it's pretty much 100%, right? You can't have rain without clouds. But now flip it. What's the probability that it's raining given that you see clouds? Definitely not 100%. Bayes' theorem is the magic that lets us correctly get from that second one to the first. Okay, enough theory, let's make this real. We're going to go right back to our medical puzzle and use this exact framework to see how on earth we ended up with that tiny, tiny probability. We're just going to follow a simple 4-step recipe. First, we'll nail down our starting belief, the prior, then the likelihood. After that, we'll figure out the total probability of our evidence. And finally, we'll put it all together to calculate our new updated belief, the posterior. Easy enough? So here are the numbers from our problem. Our big question, or hypothesis, is does this person have the disease? Our prior belief for that is just the base rate of the disease in the population, a super small 0.02%. The likelihood of getting a positive test, if you do have it, is 85%. But, and this is so important, we also know the false positive rate. The chance of testing positive, even if you don't have it, is 5%. Okay, step 3, the total probability of the evidence. This is the denominator in our formula, and it's where the magic happens. A positive test can happen in one of two ways, right? It can be a true positive or a false positive. So we just add those two possibilities together. The chance of a true positive is 85% of that tiny 0.02%. The chance of a false positive is 5% of the huge 99.98% of people who are healthy. Add them up, and you see the total chance of anyone getting a positive test is just over 5%. And now for the grand finale. We have all our ingredients. To get our updated belief, the posterior probability, we just take the probability of a true positive and divide it by the total probability of getting any kind of positive result, whether it's true or false.
And there it is. The math shows us the chance is only 0.339%. The reason it's so incredibly low is that the disease is so rare. The huge number of healthy people getting false positives completely swamps the tiny number of sick people getting true positives. Bayes' theorem forces us to take that background reality into account.
Now, this is so much more than just a medical brain teaser. This exact way of thinking is the foundation for a really common and surprisingly powerful type of machine learning algorithm. So how do we make the leap from diagnosing a disease to something like a spam filter? How can a computer use Bayes' theorem to look at all the words in an email and decide what the probability is that it's spam versus not spam?
Well, it does it by making one giant simplifying assumption. And it's an assumption that's technically wrong, which is why we call it naive. The naive Bayes classifier basically pretends that every single word in an email is completely independent of every other word. It assumes the odds of seeing the word free has nothing to do with seeing the word money.
Now, we all know that's not true in the real world, right? Words are totally related to each other, but making this naive assumption makes the math a million times easier. Instead of trying to figure out a crazy complex probability for all the words interacting together, we can just look at each word one by one.
And this really shows you the trade-off perfectly. The full-blown Bayes theorem looks at all the evidence as a whole. The naive Bayes classifier says, that's too hard. It just calculates the probability for each individual word showing up in spam and then multiplies them all together. It's a classic case of practicality winning over perfection. And you know what? This practical, naive approach works incredibly well. It's a total workhorse algorithm used for spam filtering, sorting news articles into categories, figuring out if a movie review is positive or negative, and even powering some of the recommender systems you use every day.
Which brings us to our final nagging question. If we know that the core assumption that all these features are independent is basically always false in the real world, then why does this naive algorithm work so well in so many different situations? It's a fascinating paradox, and it really highlights that in machine learning, sometimes the theoretically wrong answer is the one that's practically the most powerful. Thanks for watching.